In part 1, we built the complete cryogenic tank layout and routed the first pipeline. Today we're connecting the vaporizer, the cryogenic pump, and the gas return line while making the project look much closer to a real industrial installation. Let's continue. In the previous video, we assigned the tank nozzles according to the PNID. In this episode, we'll connect the second nozzle to the vaporizer. I aligned this pipeline with the foundation. During installation, workers can simply measure the distance from the edge of the foundation, making the pipe much easier to position accurately. Since the vaporizer connection is lower, I raise the pipeline only to the required height. This reduces the amount of support steel needed and saves material. Now I'm adding the pipe supports. Since this pipeline feeds the vaporizer, I let nature do part of the work. As the liquid nitrogen absorbs heat from the surroundings, it gradually starts to vaporize before reaching the vaporizer. Because of that, I can use simple pipe supports here. However, the supports should still be made of stainless steel, as carbon steel becomes brittle at cryogenic temperatures. Pay attention to how I place the supports. Using dynamic tracking, I position them at precise locations instead of placing them randomly. This gives us clean, round dimensions in the isometric drawings and orthographic views, making them much easier to read and fabricate. This time, I'm using the same support design but adding a steel base plate at the bottom, which will be anchored to a concrete foundation. In other projects, when I want to avoid involving the civil team, I simply use supports with adjustable legs instead. Now let's start routing the DN65 pipeline to the cryogenic pump. This pump is used to transfer liquid nitrogen from the storage tank into road tankers. Before routing the pipeline, I'll adjust the pump foundation. I'll create a 600 by 600 millimeters concrete foundation at the same elevation as the tank foundations. Now I'll search GrabCAD for a suitable 3D model of the pump. There aren't many results, so it's easier to choose one. Since there aren't many models to choose from, I'll use the skid unit and simply extract the pump from it. This is a very nice model, so let's take a closer look. On the suction side, we have an automatic valve. On the discharge side, the line already includes a cool-down line and manual cryogenic valves. By the way, I won't just use the pump from this model, I'll also reuse the valve models and the thermal relief valve. Now I'll extract the pump from the assembly and place it on the foundation. I'll place the pump in the center of the foundation and move the entire unit slightly farther away from the tank foundations to leave more space for the piping. Now it's time to convert the solid model into AutoCAD Plant 3D equipment. Since we simply picked the first suitable pump model we found, it actually fits this project quite well. The pump connections are DN40 and DN65, which match the sizes of our pipelines. For this workflow, we're not focusing on hydraulic calculations or equipment sizing, so I'll connect the pipelines directly without using reducers. In a real project, the process is different. First, you determine the required flow rate and size the piping accordingly. Once the pump manufacturer provides the final pump with confirmed nozzle sizes, you adjust the piping and add reducers if necessary to match the pump connections. I think I'll place the pump between these two foundations. If I position it next to them, it would block the truck access route, and I'd like to keep that area clear. Cryogenic pumps require special attention because they're handling liquids that are very close to their boiling point. Even a small pressure drop or heat input can cause part of the liquid to flash into gas. If vapor bubbles form at the pump inlet, cavitation can occur. When those bubbles collapse inside the pump, they can reduce performance, create vibration and noise, and eventually damage the impeller. That's why the suction line is usually kept as short and straight as possible with minimal pressure losses. The pump is also positioned below or close to the storage tank outlet whenever possible. ensuring a positive inlet pressure and helping to keep the nitrogen in its liquid state. Before any 3D modeling begins, every engineering project starts with the process requirements. We first determine parameters such as the required flow rate, operating pressure, storage capacity, fluid properties, temperature, and the overall process requirements. Based on these values, we can select the right equipment, for example, the pump, storage tank, vaporizer, and other components. Only then is the piping designed. The pipe diameter is chosen to achieve an optimal balance between pressure losses and cost. A pipe that's too small causes excessive pressure drop, while a pipe that's too large increases material costs without providing much benefit. The blue line is the suction line from the storage tank to the pump. The red lines are the discharge lines. One returns to the tank, while the other goes to the road tanker. Why are there two discharge lines? When a cryogenic pump is started, it's initially warm. As the liquid nitrogen passes through the pump, part of it immediately boils because of the heat stored in the pump components. During this cool-down period, the pump operates inefficiently and produces a significant amount of vapor. Instead of sending that two-phase flow to the road tanker, the discharge is first routed back to the storage tank. This allows the pump to cool down to cryogenic temperature. Once the pump is cold and vapor generation is greatly reduced, the discharge is switched to the road tanker for normal loading. This is exactly the same arrangement shown in the GrabCD pump model. The pump, valves, and recirculation line are all mounted on a single skid. If you watched the previous video, you may also remember that the same operating principle was illustrated in the pump manual. The pipeline geometry is almost complete, so now let's continue with the supports. As a general rule, I place supports close to equipment nozzles and near heavy piping components. We don't have many of those components installed yet, but keep this in mind as the model develops. Supports are also commonly required near branches. Valves are especially important to consider. Even a relatively small valve is basically a solid piece of metal and can easily weigh around 30 kilograms. You don't want that additional weight hanging unsupported on the pipeline. So when placing supports, don't just look at the pipe length. Always consider valves, branches, equipment connections, and other concentrated loads. Now let's adjust the support appearance to match the cryogenic design. I always check the model from all sides. I try to keep the layout clean and tidy, making sure the pipelines are properly aligned in every direction. Now let's start adding the piping components. I first try to find suitable cryogenic valves on GrabCD, but as I mentioned before, we already have several good valve models in the pump skid, so I'll reuse those. One of the easiest ways to recognize a cryogenic valve is its extended stem or bonnet. The purpose is to keep the packing and operating mechanism farther away from the extremely cold fluid, where the temperature is much higher and the components can work properly. For shut-off service, I'm using ball valves with welded ends. Why welded ends instead of flange connections? Flanges can certainly be used in cryogenic service, but they require more attention. You assemble the flange at ambient temperature, and once liquid nitrogen at around minus 180 degrees Celsius enters the system, the piping, bolts, and gasket all undergo significant thermal contraction. This can change the gasket compression and may require checking or retightening the connection during commissioning. With welded connections, there is no gasket joint to worry about. You weld it, inspect the weld, and basically forget about it. Until the valve breaks, of course. Now I'm looking for a cryogenic expansion joint. It basically looks like a flexible corrugated metal section, usually called a metal bellows expansion joint. When the pipeline cools down from ambient temperature to around minus 180 degrees Celsius, the metal contracts and the pipe becomes shorter. In a long or restrained pipeline, this thermal contraction can generate significant forces and stresses. The bellows can flex axially and, depending on its design, accommodate other movements as well. This allows the pipeline to absorb some of that thermal movement instead of transferring excessive loads to the piping, supports, equipment nozzles, or the storage tank. And because we're working at cryogenic temperatures, the expansion joint must be specifically designed for cryogenic service. It's not just a random flexible piece of pipe. I'm going to rearrange the truck loading line in the same way I did with the pump. I want to keep the truck access area as clear as possible. Now that I'm editing the video, I can already see one thing I would change. I would place this expansion joint closer to the pump. And this happens sometimes in real design work. When you've been working on the same model for hours or even days, you don't always notice every questionable decision immediately. Then you come back the next day with fresh eyes, look at the model again, and suddenly you see things that should be improved. That's completely normal. Engineering design is an iterative process. You model, review, adjust, and sometimes change decisions you made earlier. On the discharge line, I'm adding a check valve to prevent reverse flow when the pump stops. I'm simply using one of the standard AutoCAD Plant 3D valves and changing its appearance to represent a simple wafer-type disc check valve. Unlike the welded shutoff valves we used earlier, this valve is installed between flanges. A check valve has an internal moving element, so it may require inspection, maintenance, or replacement during its lifetime. Using a wafer-type valve between flanges makes it much easier to remove and replace without cutting the pipeline. I don't really like this large piping assembly with so many components and so little support. There are several valves and fittings concentrated in one area, which adds quite a lot of weight to the pipeline. So I'm going to rearrange the supports and provide better support around this assembly. Now that all the piping components are in place, we can move the pump closer to the pipelines and closer to the storage tank. This reduces the overall pipe length and, more importantly, keeps the suction line shorter. For a cryogenic pump, that's especially beneficial because a shorter suction line means lower pressure losses and less heat ingress, reducing the risk of liquid nitrogen starting to boil before it reaches the pump. For truck loading, a flexible transfer hose is normally used. In our case, a hose specifically designed for cryogenic service. Modeling a realistic flexible hose in AutoCAD Plant 3D is not very convenient, so for this model I'll simply add a flange connection point and leave it there. In a real installation, the end connection depends on the loading system and the tanker. Instead of a standard bolted flange, you may have a dedicated quick connect coupling that allows the operator to connect and disconnect the transfer hose much faster. One more small element to add: a filling connection for small liquid nitrogen containers, for example 5-liter vessels. For this connection, I'm using a DN15 branch with the same type of cryogenic ball valve. I take this branch directly from the liquid withdrawal line, upstream of the pump. For filling such small containers, we don't need the main transfer pump. The pressure inside the storage tank can provide the required flow. Of course, in a real installation, this filling point would need additional details depending on the operating procedure, such as a suitable filling connection, safe venting, and protection against trapped liquid. One more very important device is the thermal relief valve. In cryogenic piping, liquid can sometimes become trapped between two closed valves. If that trapped liquid starts warming up, it expands very quickly. Because liquid nitrogen is almost incompressible, even a relatively small temperature increase can create a very large pressure rise inside that isolated section of pipe. The thermal relief valve protects the pipeline by opening at a preset pressure and releasing a small amount of fluid before the pressure becomes dangerous. So whenever liquid can be trapped between two isolation valves, we need to think about thermal expansion and provide pressure relief. And I think this is a good point to stop for today. The main piping geometry is now in place. We've added the pump, supports, valves, expansion joints, and some of the important safety components, but the project is not finished yet. In Part 3, we'll continue developing the model, add the remaining details, and bring this cryogenic installation closer to a complete, real-world design. If you enjoyed this workflow, subscribe so you don't miss the next part. Thanks for watching, and I'll see you in Part 3.